Thank you very much. It's really great to be here. I was surprised about the invitation, and when I saw what body of work was done on positive programming systems, I found it very interesting. Let's definitely go and study some of that. And I was told that maybe that was apparently the idea of the organizer. It might have something to do with something they want to do. So I would like to present to you a rather conservative thought, I would say. It's much less ambitious than the wonderful things we saw before this morning. First of all, it's all based on classical considerations.
Thanks. It's all based on classical considerations. So constructive gravity, it's all about classical models of matter and gravity. And yes, we're always talking a lot about fundamental physics, but ultimately, obviously, physics is phenomenology. And then our best phenomenology, maybe we call fundamental and have ideas about it, but that's of course it. And what we in the classical domain say is we need a matter model, we need a gravity model, and if we formulate them in terms of actions and we add them up, we have the action of the universe, and that's our theory. That's all doubtlessly so, and was very, very successful up until general relativity, including Maxwell theory and things like that. All right, but what you of course need to do, you need to postulate the action for the matter fields, and you need to postulate the action for the underlying geometry. And essentially the history of the standard model is that we keep postulating, or people kept postulating actions until the phenomenology that was also increasing was a little bit like what Renate Loll said in her talk. There's a longer and longer list of things you wish to have, but here they actually came from experiments. So it was not a wish list, it was a demand list. And obviously we're very used to tinkering with the standard model and coming up with things to make it work. And the history of general relativity is, first of all, Einstein told us so. That all worked very nicely. And yes, one can consider alternatives, and well, maybe now more so, but they're not mainstream. So, and maybe for good reason, because general relativity is a rather rigid theory, and above all, the standard model, of course, is constructed such as to work together with a Lorentzian metric spacetime. Okay, so in a sense, it was more like once we had the gravity action, the rest had to follow suit. It's the old observation of Einstein: everything shall be done in the image of Maxwell theory, so to speak. All right, so that's that situation. And now what is constructive gravity? Constructive gravity is a game. It says, let's constrain ourselves to the game that we only postulate the action for matter fields. And then the essential statement is, but of course it comes with many asterisks, you can actually obtain the gravity action from the matter action. So that's also the central result. Well, provided physically weak, that's of course public relations, physically weak assumptions hold, mathematically they're absolutely necessary. And then we obtain, very roughly speaking, the action, or rather the Lagrangian in the action, as a solution of a PDE system. So that's kind of the promise. And what's the mechanism behind this? How would that work? And the mechanism behind it is that the matter equations and the gravity equations, they must have some common canonical evolution. So they must share Cauchy surfaces. And if you give the initial data for the matter and for the gravity on the same hypersurface, which you anyway need because the matter action obviously, well, not obviously, but typically has a geometric background. And then the idea is they must evolve together in lockstep. Now that sounds like a rather weak condition, and it turns out it's much stronger than one thinks. Now I would like to draw your attention to the fact that I didn't have caps lock on when I wrote the space-time metric with the capital G. It's supposed to indicate we might take in this approach any tensorial background. So it could be a non-symmetric metric, if you wish. It could be two Lorentzian metrics, or maybe non-Lorentzian metrics. It could be just anything, just not anything will satisfy these physically weak assumptions. All right, but the idea is, and we will show that from, if you start with Maxwell, you get Einstein and say, okay, we knew this. But the point is, the whole thing gets more interesting by saying we take it in this much more general context. So the change is we do smooth manifold is the basis and so on, but then some tensor fields, one or several capital G, and some matter fields, and then we start going. All right, so the next thing is we didn't do so much because most of this connection in this direction was already there in the literature. I'll come to this in a second, but there was some bits missing. They were not entirely trivial from our point of view, but then if we insert them. So our work is little, and we're of course on the shoulders of those who did stuff before. But let's do a warm up, and that's kind of the baby problem. How do you start with Maxwell theory, that would now be down there, and get Einstein gravity? And one, of course, historically, let's start up there with Einstein gravity, because obviously you can, by hook and by crook, you can argue why you want this gravity action. Well, all right. Now, obviously, in the 60s, the latest, people started asking what's actually the evolution behind all of this. And we all know that. We saw it this morning. Thomas Thiemann nicely reviewed it. There is an initial value formulation where you now understand how the metric and its Lie derivative time direction actually evolves in time. What is actually evolving is, of course, the ADM formalism. And so there you think of your metric. This is now really, now we have down here, we want to connect. We have here the background metric, and we project it on these hypersurfaces, and we can now study the evolution of these three metrics. Now, that once you have then the decomposition of the Hamiltonian into this super Hamiltonian and super momentum, you can actually calculate this constraint algebra that also was already shown this morning. And indeed, it's not an algebra because it doesn't have structure constants. It has structure functions because they're the inverse of the spatial metric, depending on your foliation, what you pull back there, appears in there. And that makes this a mathematically much more unwieldy object. But anyway, that is what it is. And actually, it started with Kukash in the 1974, where it became clear this is really, once you have this algebra, you can really argue backwards under the standard assumptions that your Hamiltonian must have that shape. So there is an alternative formulation in terms of the constraint algebra. And then really something, and that hint I owe to Christina Giesel. Back then, we were working together, and she knew of this paper by Hochmann, Kukash, and Teitelbaum, Geometry Dynamics Regained, where the question was, well, can I start from here? Well, how do you know the algebra? And the basic idea is, if you forget about all these dynamics, important now, forget about all these dynamics, look at hypersurfaces in a Lorentzian space-time and study by these operators. It's now not the blue D, these are other operators, D and C. These are deformation operators. So in the direction of the normal vector, but that will be important, you can actually do normal deformations with this operator of functionals of the embedding function. And with these guys, you can do tangential deformations. And if you then take this algebra of deformations on functionals of the embedding function, how you orient your embedding, your hypersurfaces, then you find an algebra that looks precisely like the constraint algebra. It's a very famous result, Hochmann, Kukash, Teitelbaum, 76. And they said, hey, we only need to know how Lorentzian manifolds work, in particular, how from a hypersurface, if you have it embedded, you have canonically only a covector, normal covector. You need to flip it into a normal vector. Lorentzian metric, not a problem. We do this. Okay, fine. So they gave this reformulation. Now, that was already the work that needed to be done, but this is all in a metric setting. So this is the geometric algebra reformulation of the Einstein action. So this all seems to depend up here on the Einstein action, but that here says, no, 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 no. If you have this embedding, you get this, but if you get that from there, you get the Einstein action. All right. Now, something that sounds entirely unspectacular, and I already said it, how do you get from your normal covector that is natural with the embedding, how do you get the normal vector? Well, yeah, you pull the index. It's not a secret. You pull the index with the big space-time metrics. It's not the small metric, the induced one. It's the big space-time metric. You flip up the index, and then you can normalize. That doesn't seem particularly impressive. Nevertheless, this can be generalized, I'll say later, and this was a paper with Christina Giesel and Matthias Wohlfahrt. In any case, we'll come to this later again. This is something, yeah, we'll call this a Legendre map. So if you have these cones, that's the thing. Of course, these cones come from a double cone, and this double cone has a null surface. There we have an algebraic variety. This is a very simple example. And the point is underlying this. And again, in the metric case, you say, what is the man talking about? This is a very simple thing. This is a polynomial that you get by putting two covectors into the inverse metric. Doesn't seem particularly impressive, but nevertheless, it's true. And the point is, how do you get this? Where do you get this polynomial from? And the storyline is, if you have Maxwell theory, you can, of course, calculate its principal polynomial, which gives you the causality of the theory. And this principal polynomial, there is somehow an arrow missing down here. If you take this principal polynomial, that principal polynomial of Maxwell theory gives you also the hypersurfaces, the Cauchy surfaces for Maxwell theory, but it's the same one. If you now require that it's the same one as that for gravity, then you get the shared evolution. Okay? This is also trivial because we're so used to doing this, but there is this, the structure is important. So we can, therefore, here we have equivalences, so to speak, but here starting from matter, we get the principal polynomial of the matter. We can then lift indices, so to speak, and then the rest goes straight up here. But the important nexus here is that we really say they have the shared common evolution. All right, this was for a Lorentzian metric. So in that, for these reasons here, Maxwell theory, if you write down Maxwell theory for that background, what dynamics do you need to give this background so that the total dynamics is compatible causally? Einstein. Now, the interesting thing is the general case. So the general case is I have some matter field, say also tensorial, on a somehow given tensorial geometry. Forget that word for a second. Okay, no, I can't forget it. Okay, so if you have that for that matter theory, please forget quantizable, a classical theory, and you can calculate the principal polynomial of that, and that will in generally be not a second order polynomial. It will have higher order, a higher degree polynomial, and now you really need some properties of this for all the further, and that is if this hyperbolic polynomial must be hyperbolic. That's kind of expected because we want some Cauchy evolution. But there's also something called the dual polynomial of that polynomial, and that one must be hyperbolic too. If that is the case, and then little asterisks I'm not talking about here because it's not the main point, then you can erect this whole building again for this much more general case. And why I write here canonically quantizable, this is just, it's again public relations. If you want to canonically quantize, you need to make a positive and negative energy split. You need to be able to make it, right? And essentially translated into this polynomial, the dual of this polynomial must also be hyperbolic. That's the idea. Okay, so we could say this without quantizable. We just need this action to be such that the principal polynomial is hyperbolic and the dual is also hyperbolic. And that would, for instance, if you start with a pseudo-Riemannian metric, immediately kick out anything that's not Lorentzian. Well, that hyperbolic would suffice. Dual hyperbolic is then for more complicated geometries, and I will give you an insight on that, an example. Now, this Legendre map, raising the index before, how is that done? And that was the hard work. So this paper with Sergio Rivera and Dennis Retzel in 2010, we really studied these bihyperbolic polynomials. And then you find actually a unique hyperbolicity cone for the whole theory, even though the polynomial may be higher degree and so on. And for what we need right here, you find you can do this with, from this polynomial follows how you actually raise and lower the spatial index here. That is highly non-trivial in the general case. In the metric case is what we all know. And then indeed from here, you can then calculate this deformation algebra and this deformation algebra, but now with this remnant here that remains from the non-trivial geometry, but it's this symmetric polynomial. This can be any tensor, but the symmetric polynomial, you can go up here and you can find, if you are able to find here the, in quotation marks, representation, because again, it's a bit more complicated, it's not just a representation of a Lie algebra, you can then find the gravity action starting down here. And the construction equations are that if you start with the action, you calculate this polynomial, then you can immediately write down from these data, you immediately construct countably many PDEs. That's another dirty secret, because there is not particularly good theory for a system of countably infinitely many PDEs, certainly not for what we want to do. But this reduces to that. So the first statement is, if you give me your exotic matter theory, and who knows, maybe we need one day, that is so exotic that it requires a non-metric background. Okay, so for instance, 2 Lorentzian metrics would be exotic, definitely. You calculate this principal polynomial and you get the gravity action that can underpin where the dynamics of this G underpins the background of the matter action you dreamt up. If you say that never comes up, then this is of no further interest than connecting it nicely. If you say that might come up, this might be extremely useful to see this. Now, yeah, these equations, these blue guys are coefficients. You can all calculate directly from the principal polynomial. Now, the red stuff and the blue stuff is what you're solving for. It's expansion coefficients of the Lagrangian. It's obviously messy, but we can do it for Maxwell. Actually, Kukash and Teitelbaum do this with nice, use a little bit of Lovelock's theorem and so on. They already did this upper part. But if you want to do it, saying, I really restrict myself to, I pretend I know nothing about geometry. I have a metric and I have a manifold in the metric, but I have no deeper insight. I have not Lovelock's theorem. I don't know anything about curvatures. I don't know any of this. Put yourself in that position, a little bit maybe like Einstein before he learned Riemannian geometry. And then you can nevertheless follow this path purely by solving these PDEs. And the curvature tensor that you need pops out in the metric case. And in non-metric cases, what is anyway curvature? Okay, but so if you restrict yourself to that, you can derive this nevertheless. And this was done by Florian Wolz here in 22. He finished that work with his PhD thesis. That was quite impressive. There's a lot of mathematical subtlety going in. In particular, you need to be very careful of whether the equations you work with are involutive, because otherwise all kinds of hell breaks loose. All right, so case study, quick case study. What could you do, for instance, just to illustrate it a bit more? Let's say we do a refined Maxwell theory where it's not one single Lorentzian metric that ties together your F's in the action, but it's 1/4 rank tensor G, and that can produce already in the geometric optical limit birefringence. Okay, you can have birefringence anyway as a second order effect, but if you're in the purely geometric optical limit, want birefringence in space-time, in vacuum, and you still want to remain linear, then this is essentially the most general thing you can write down. Okay, so I mean, little fantasy would be if tomorrow we saw in the sky, of course, fantasy, a light ray that splits into two, and it's not a second order effect, it's just at pure ray optics splits into two. The Lorentzian metric couldn't underpin the electrodynamics that does that, but this one could. So we have a fourth rank tensor. You see it has induced symmetries, a little bit like the Riemann tensor, apart from the cyclicity. Can we find an action for this fourth rank tensor that can underpin these dynamics for matter such that the combined dynamics are make causal sense? So can we write down general relativity, but gravity for such a geometry? Now, if I ask you that question without all of this, you say, well, we probably have to find some invariants and write them down. And hey, you can do all of that, get a big ambiguity, of course, if you can do it at all. But my main point is, by having this could come from observation, the fantasy. Okay, kind of another observation of something exotic where you need some other background. But if this describes the phenomenology well, then you have a hint from nature of what on earth to write down there. So that's the hint of nature. For Einstein, it was Maxwell theory, was the hint from nature, and then you have to go up here. So in 2000, was it 2010 or something, when in the Gran Sasso, they measured the neutrinos that were faster than the speed of light, which turned out to be a plug improperly put. Actually, Hermann Nicolai came into my office and he knew I was working on this crazy non-mainstream stuff. And he said, can you do that? Well, if there will be a nice phenomenological model for those neutrinos, that might actually be non-metric. It could still be that the principal polynomial is just what it normally is. But if it's not, yeah, then we probably can do that somehow. Okay, good. So yeah, you arrive up there, or people speculate about bimetric theory, and it immediately starts with considerations. What is the light directions? What is the time-like directions? Well, this theory of this principal polynomial, this is this early paper in 2010, tells you all of this. You may have two metrics here, and they may be both Lorentzian, but these two Lorentzian cones may actually. Okay. May actually stand on top of each other, and then it turns out this here is the correct hyperbolicity cone, right? And then that will essentially determine this principal polynomial, etc., etc., etc. Okay, so you can start here. Here, the principal polynomial for this particular theory is cubic in G. That's quite something. That two epsilons here that has been calculated by Rubilar and Hehl and Obukov long before we looked at these things. Yeah, and then you go through the whole motions, you calculate these coefficients, you plug them in here. Nobody wants to do that, but it can be done. Yeah, and then you have to solve these equations. And as I said, we could only solve with this self-restriction of knowing no geometry. We could finally do it. Florian Wolz essentially did it. Starting with Maxwell theory or the standard model. Actually, the whole standard model action is built to only produce this polynomial. So the Dirac algebra, gamma mu equals 2g mu identity, that is actually the statement that the principal polynomial here is the standard one. So everything is built like that. But what if we can't afford that anymore? What if we need a new background or matter with a metric background that is so complicated that also the polynomial changes? So there's this paper, very well-known paper by Velo and Zwanziger, where they say, let's study Maxwell theory, well, Broca theory with a mass, and also add a fourth order a mu, all squared term to it, a quartic self-interaction as a theoretical consideration. And they find very quickly that they get causality problems. Why is that? Well, the point is that theory, if you derive the equations of motion from the action, you get, or write an equation of motion, but it's not involutive. If you make that equation of motion involutive, you see that some of this, for instance, some of these lowest order a mu a squared term, the coefficients, they move up to the highest order derivative, which makes this polynomial, and they get something like GAB times GCD plus ACAD. So there is effectively a fourth order polynomial, but not like this one, that they get, and they say, and therefore this is sick, we should never do these a mu squared terms and all of this. I think the conclusion of that paper is not entirely correct. Well, one can use it in a correct way, but what it actually says is that theory that you wrote down simply doesn't have standard causality. Okay. Anyway, so you could do all these things. So what can be done? Well, if you want to solve them exactly, that's very hard. And so for a short while, we tried to solve it for this nice example with this birefringent electrodynamics. The point is, this is so hard, I would rather wait for a worthy matter action to really throw resources at it to actually solve that. Might still not be possible. Now, perturbative solutions. Oh, did we have beautiful hopes? We did that and we calculated them. And then you get here big Lagrange. It was horrible. But the point is, this whole thing has only 9 gravitational constants, if you do this for this birefringent electrodynamics, that need to be determined by experiment. If you were in the linear case only, if you were to guess what is all possible, you would have 136. So this reduction in what you have to measure comes all from the insights of this compatibility. Okay, so right. But there's a problem, a dirty secret of this perturbative thing. These equations come from these 3 constraint equations. No? The D with the D, that's fine, you solve it. The C with the D and the C with the C. And this last one, the CC bracket, that's the equations that come from that one. Those equations, we could not show that they are already in involutive form. For the other accountably infinitely many, we could show it. For those, we couldn't. And then the problem is, if you have equations of motion that are not in involutive form, and you make a perturbation ansatz to first order, you get nice coefficients. If you then make one to second order, the first order coefficients might get corrected. Well, that's not what we have in mind, right? So that means the first order was not properly calculated. And that is, of course, quite a task. As I said, there is not, at least not known to us or mastered by us, but I think there is no theory for PDEs that would go for involutivity for an accountable set of PDEs. It's a mathematical problem. We don't know how to do this. So reliable perturbative theory would hinge on the involutivity of H equals D. And one could then say, solve it for highly symmetric cases, so Schwarzschild's idea, and so on. That is feasible, but that's also quite involved. This has been done by Maximilian Düll. He succeeded for the cosmology, so to speak, mildly interesting. What comes out, I mean, yeah, but it's not already for the static spherically symmetric case or something, it's impossible. All right, so the conclusions are canonically quantizable matter or actions that satisfy the corresponding assumptions to get a bihyperbolic polynomial. They imply the dynamics for the geometry you assumed in your matter action. That can be done. The assumptions about matter, therefore, or the insights about matter from experiment, phenomenological observations, once formulated reliably, can be translated into gravitational insight. Now, the mechanisms is canonical evolution, surprisingly. And yeah, it's, the practical implementation only requires standard techniques, but it's very difficult. Yeah, that's the hard step. Open problems and partially open problems, an exact solution is unsurprisingly hard, although these are linear PDEs, okay? But the problem is they're not finitely many. And indeed, nevertheless, a gapless solution, also much more refined and to the point than Kuka-Streitelbäum, well, in hindsight, for standard model matter is by Florian Wolz. And yeah, the perturbative solutions would be very interesting. But again, if we have a worthy matter action, I think it would be worth throwing some resources at it. Thank you.